We've been talking about the law of sines and the law of cosines as useful tools, but they're more than tools. They're more than these arbitrary things that we've come up with. They actually have some standing in mathematics. The thing that's nice about mathematics compared to other sciences or other arts is that what we do in mathematics, the tools that we have, are inherently verifiable. They're things that are true not because somebody says they're true, but because they have to be true. And that goes for the law of sines and the law of cosines as well. So I thought I would give you a little proof along the way for what makes the law of cosines work. So think about starting with an arbitrary triangle. Maybe you draw a triangle. It doesn't have to be a right triangle, just a standard thing where you label things A and B and C and sides opposite A, opposite side, opposite angle A, side B, opposite angle B, and side C, opposite angle C. The question is, what is it about the relationship for the lengths of the sides and the sizes of the angles makes the law of cosines true? So let's sort of think about it relative to angle A as being like the base angle for the law of cosines. And a way to get at it is to treat this as a situation where we're going to use the right triangle trigonometry. So this is an arbitrary triangle. Let's make a right triangle by dropping an altitude. And that could be the side H. And say it hits the base here at capital D. So there's a right angle there. And that would be the setup that we've got. And now maybe we can keep track of that side C so that there's the part of side C that goes with the triangle on the left. So maybe this part is X. And on the other side, the rest of the side C would be C minus X. So if it's set up like that, X and C minus X, we've got tools available for right triangle trigonometry. For one thing, we can say on that triangle on the left so that would be A, D, C, that the sides are X and H, and the hypotenuse is B, and the Pythagorean theorem says that x squared plus h squared is b squared. So there's one little piece of information. And the other thing we can do from the analysis of trig functions is to say that the cosine of angle A is the side adjacent over the hypotenuse. Side adjacent is side X, and the hypotenuse of that little triangle would be B. So we could say that X is the same thing as B times the cosine of angle A. Now, from the other triangle, the one BDC on the right, we've also got that where the Pythagorean theorem holds. There the legs are C minus X, so C minus X squared, and H squared. So C minus X squared plus H squared is the hypotenuse of that little right triangle on the right, so that would be A squared. So that says that A squared is equal to C minus X squared, so C squared minus 2CX plus X squared. And X squared is X squared plus H squared. So that's the same thing as C squared minus 2C. We've got, we know what X is in terms of the sides of the triangle. That's 2C times X, that's B cosine A. and 2cx, and then x squared plus h squared. X squared plus h squared is b squared. So out comes all the pieces that we have to say that a squared is b squared plus c squared minus 2bc cosine a. So the law of cosines pops out of, for an arbitrary triangle, pops out from doing the definition of the cosine and a couple artful applications of the Pythagorean theorem after we've built these left and right triangles inside. Now you always have to be careful when you write something like this that you haven't built in assumptions that aren't warranted, or you're working with extra information that the picture provides that you might not be entitled to have. So the one possibility that would break this setting things up in terms of x and c minus x along the bottom would be if the angle A happened to be not this acute angle, but were an obtuse angle. Suppose the triangle were set up like this, so that now it's still A, B, C, but now when I try to drop my perpendicular, the perpendicular that I drop doesn't hit on that side of the triangle, rather it hits on an extension of the triangle. So if that happens, probably the right setup would be to think about this as maybe this is still the x, and then to get this is C then, still A, still B, and so now the setup is going to be not C minus x as in that upper picture, but C plus x. But you can still probably see two right triangles inside that triangle by dropping the perpendicular, and that relationship between the trig function definition still works to give the right value for the sine, right value for the law of cosines that works. So that's sort of a little background to let you say in confidence, when you apply the law of cosines to solve a problem, you are not doing something that is arbitrary. Rather, it is as much part of the underlying structure of trig as is any other thing you might have done in the course.